So in today's talk, I'm going to present an alpha potential game framework for dynamic n-player games. And this is a topic I have been working with my collaborators for the last 2 years, roughly speaking. So the talk is based on these following three works. It will, in the first two papers, we are essentially lay down the theoretical foundation of this alpha potential game framework. They are both basically these two papers are together with Xingguo from industrial engineering and operational research from in UC Berkeley, and also Xinyu Li. When we work on this project, Xinyu was a PhD student of Xin in Berkeley, but now Xinyu is currently doing a postdoc in Oxford. So the third work is essentially more like extension or application of the theory from the first two paper. We are together with colleagues with Anran, who is currently an assistant professor at Columbia, and also her colleagues in civil engineering in Columbia. We are essentially applying this framework to automated driving. So a quick introduction, as we already know, the n-player games plays an essential role in finance and engineering. For example, you can think about in a production management, maybe there are several firms, they are producing similar products. And then basically each of the firm control the production speed of their own production line. But then the overall price of this product will depend on all firms' production. So basically total amount of the of the firm. So in this case, that each firm they need to decide how much they produce, and there is a competition between how much they are going to charge for their products. A more concrete application is also appears in market microstructure. In this case, that basically there are n traders. They are essentially balancing their inventories, so they can decide how much they want to sell or buy a particular asset. But then their joint trading strategy will impact the market price, and as a result, they are going to impact their own P&L. This also applies in engineering, particularly automated driving. In this case, you can think about there are n cars. Okay, so then each car they want to go to their own their preferred target, maybe at a certain point. Okay, maybe either they want to go to the target as quick as possible, but they are driving on the same road. In this case, when they want to decide which direction they are going to they are going to drive, they are also going to ensure safety, which means that they are going to be away from the other cars. So in this case, you can think about there is a competition between different cars, and they are competing for the space, and they want to go to their preferred target as quick as possible. So in all these applications, you can essentially formulate this problem in terms of a dynamic game. And then each player, they are n player. Each player, they interact in some common environment. Typically, it can be stochastic, and they optimize their individual objectives. In this trading problem, maybe it's each individual's performance and loss on the risk. And then in this automated driving, it basically depends on how quick they are going to go to their preferred target. So in the case that if all the players have the same objective, then this is typically known as a cooperative game. And then typically people are interested in what is the solution is essentially given by some social optimal, or it is known as a Pareto optimal. And it is known that in this case that you can essentially solve this game as a control problem because everyone has the same objective function. And then we have a reasonable understanding about how to characterize the solution and how to compute them numerically, even though there is a large number of players. The situation is more involved if all the players have different objectives, and which is essentially the competing objectives, which is essentially the appears in all the three applications I mentioned before. In this case, that we typically focus on Nash equilibrium, which is essentially which is a set of strategy where given the strategy of other players, no one has incentive to deviate from this given strategy. In the sense that you can think about at the Nash equilibrium, all the players are essentially doing best response to the other player's strategy. And as you can see that from by the definition of the Nash equilibrium, there is a strong coupling between all the players' strategy at Nash, which make the computation of Nash challenging. In fact, it is known that in the worst case, computing the Nash equilibrium, the complexity of computing Nash equilibrium increase exponentially in terms of the number of players. So this is a very intuitive. What it means is that if each player can choose their action within certain set A, maybe there are they can choose five actions. Then if there are n player, then the total number of possible actions just become 5 to the power n, which essentially shows this exponential increase. So even though we are able to conquer this computational complexity, it is also known that there is typically there is no good algorithm for computing Nash equilibrium, in the sense that many natural iterative algorithms may fail to converge to Nash equilibrium. For example, one of the natural or popular algorithm is called a fictitious play. In this case, that in order to compute the Nash equilibrium, what you can do is that it is iterative algorithm. For each iteration, you look at what the history about the other player's strategy, and each player try to do a best response to the history of the other players, the historical action of all the players' action, and then you iterate it many times. And in the two-player zero-sum case, it is known you can show that such a iterative algorithm converges to a Nash equilibrium. But in the non-zero sum, in the sense, or for the general sum case, even in the two-player case, there is a famous counterexample by Shapley to show that such a iterative fictitious play algorithm does not converge to a Nash equilibrium. And then in the dynamic game, you can imagine that things become even more involved. And then basically, recently by a group in UC Berkeley, the people observed that even in the simple linear quadratic case, where all the players doing using a gradient descent to optimize their objective function, then in this case that the corresponding algorithm does not converge to the Nash equilibrium. So because of this difficulty in analyzing the Nash equilibrium and computing the Nash equilibrium, people essentially start to look for structure of the game so that this Nash can become the analysis of Nash and the computation of Nash become easier. So one of the popular framework or established framework in our community is essentially this mean field game approximation. In this case, that we essentially focus on a class of game where all the players are homogeneous and weakly interact. By homogeneous, I mean that each player, they essentially have the same, they are dynamic, have the same characteristic. Maybe if you consider a continuous time differential game, then everyone has the same drift and same diffusion, and they have essentially the similar objective function. Another important property is the weak interaction. In this case, it's essentially assumed that all the players are essentially, instead of depending arbitrarily on other players' state, they only depend on empirical distribution of the other player state. So because of this weak interaction, you can essentially, heuristically, you can essentially send the number of player n to infinity. In this case, that as there are sufficient large number of players, essentially, you don't care about any individual player's position. You only care about the aggregated behavior of all the other players' position. In this case, the game simplifies to a game of the representative player and also the corresponding mean field distribution. And this allows you to simplify the computation of the game. Of course, that in practice, this weak interaction is a strong assumption. Homogeneous is a strong assumption because that in general, people may have different objective functions, but the weak interaction is also a strong assumption. For example, if you think about in the automated driving applications, which I'm going to show you in more detail in the later part of my talk, even though you have many cars in a road, okay, as an individual driver, I still care about a lot about the cars which is very close to me. Okay, so basically there's the cars which is the closest cars impact on me is still not negligible. Okay, so in this case, in order to ensure safety, I not only care about the overall distribution, but the cars which is close to me has the impact of the cars which is close to me does not vanish. Okay, so this essentially break the assumption of the mean field approximation, and then which essentially means that the mean field approximation cannot be applied in this case. So our framework essentially try to capture a richer game structure instead of basically by trying to remove this weak interaction and homogeneity assumption. And then we are also going to study the n-player problem instead of only focusing on the limiting behavior as n to infinity. So to motivate this alpha potential game framework, let us go back to the root about these things, which is essentially is a static potential game. Okay, so this framework was proposed by two economics, Moderer and Shapley, in 1996. Okay, so in their paper, they essentially consider a static game where there are n players. So I use this index n to denote the number of players. Each player take action within a certain set AI. Okay, you can think about this AI to be finite set or some set in RD. And each player's utility depends on, I'll try to optimize their utility, which depends on all players' joint actions. Okay, so right now this formulation is just a generic formulation of the static game. And then in order to, what they study is that they study a subclass of the static game, which is they call the static potential game. In particular, what they assume is in this game, there exists a common function, phi. Okay, so the key thing is this phi depends on the all players' joint action, but this is independent of is independent of player. Okay, and then this potential function satisfies this identity. What this means is that for any player I, okay, if the player I unilaterally deviate her action from AI to AI prime, the change of player I's utility is equal to the change of the potential function. Okay, so right now, if such a function exists, then they call this game a static potential game, and then the function phi, this common function phi, is called a potential function. Right now, it is just an algebraic property. Okay, and then at this moment, there is no assumption about the homogeneity, or in the sense that all players can have different action set. They can have a different utility function. So this framework, once this framework is introduced, this become a popular framework for analyze static game. Because of this, being a potential game has two important advantage. Okay, so the first is that because of the structure of the potential function, you can actually show that any optimizer of the potential function become a Nash equilibrium. For example, if in this case, in utility, if you want to maximize, you can show that if you find the maximizer of the potential function, because of this identity, no player has the incentive to deviate from the maximizer. So in some sense, if you know a game, a static game is a potential game, then finding Nash equilibrium becomes the optimization problem of the potential function. So in the sense that you can essentially leverage on this game becomes this n-player game become a single player optimization problem, and you can leverage on many existing optimization tools in order to compute Nash. Another advantage is that, as I showed before for generic game, there is no the typical or some natural algorithm may not converge to the Nash equilibrium. But if you know a game is a potential game, or if there is a limited potential structure, then suddenly you have many algorithms. You can show many algorithms can actually converge. And this include the best response algorithm or the fictitious player algorithm, which I introduced before. It also include a policy gradient algorithm in the multi-agent reinforcement learning. The reason is just that basically this potential function allows you to control the unilateral deviation of each player's strategy, and you can more or less intuitively you can show that all these you can leverage on the structure of this potential function in order to analyze the convergence of the algorithm. So Okay, because of all these advantage of the static potential game, then the very natural question is that can we essentially apply a similar framework to analyze the dynamic game? Okay, so I will present a more precise formulation about what I mean by dynamic game. But you can think about in this case that each player try to optimize a cost function, but the cost function is induced by an underlying dynamical a system over a certain time horizon. And the system will evolve over time, and the evolution depends on the current system state, and can also depend on depends on players' action. And in the particular self-driving cars, you can think about the system is essentially the position of each car, and then basically they want to the direction is that the control is that you are able to change the direction of the each car, and then you want to reach to your own objective function, but your own target, but on the same time avoid collision with other cars. So this concept of potential game has been applied to the dynamic game, particularly by starting by a group of computer scientists. So they essentially introduced this notion about a Markov potential game for discrete time games, where essentially each player consider underlying discrete time Markov chain, and with a finite state and finite action, and they try to optimize over Markovian policies. What they do is that they just directly generalize the static potential game to this dynamic setting, in the sense that they assume that there exists a common function phi such that the change of each player's utility function is equal to this change of the potential function phi. And as you can imagine, basically you have the same advantage in the sense that any minimizer of the this potential function phi become a Nash equilibrium. And then if you know a dynamic game is a Markov potential game, then many algorithms converge to a Nash equilibrium. Of course, however, there is a limitation about this this concept about Markov potential game. In fact, I think the main issue before our work is that in the community, it is difficult to verify whether a game is a Markov potential game or not. Okay, so there is no good criterion to verify given a dynamic game whether a dynamic game is a Markov potential game or not. And in all this existing literature for the dynamic game, they typically assume they assume a game is a Markov potential game, and then to say that they studied the corresponding learning algorithm. However, it is known that in many dynamic games are actually not a Markov potential game according to their notion. In particular, even though you assume that each step you can see a dynamic game, where each step, the reward function or the instantaneous reward function, instantaneous cost function is a static potential game, because of the underlying dynamic nature, the overall dynamic game is not a Markov potential game. So that's why it is a challenge to verify whether a game is a Markov potential game or not. And in particular, in many cases, it is not. So from this discussion, it seems that in order to study a dynamic game, seems that a more general form of the potential game is necessary in order to analyze dynamic game. And this is essentially what we are going to do in our work. So in the first paper with Xin and Xingyu, we consider an abstract framework where we consider the abstract dynamic game G, where there is a underlying state space S. Okay, you can think about the state space is RD, where essentially this is the corresponding the space where the space where the state dynamic evolves. Each player try to optimize certain strategy set AI, and then they try to minimize the corresponding cost function JI, which depends on all players' joint control strategy. In this case, this is a very generic formulation of the dynamic game. For example, if you consider a stochastic differential game, stochastic differential game, you can think about this JI will eventually involve an integral form of the corresponding underlying a controlled SDE, and then this corresponding control may be just some adapted stochastic process. I will make this cost function, definition of the JI in a more precise way. But right now, it is just a generic framework where the AI is a arbitrary infinite dimensional set, and then the ji just some functional mapping from the joint control strategy to a real number. In this case, we introduce the concept about alpha potential gain, in the sense that we assume there exists a function phi, so that the phi essentially predicts the unilateral deviation for any player up to an error alpha. Okay, and if such a function phi and alpha exist, we call this function phi alpha potential function, and we call this game alpha potential game. Okay, so you can think about this. You can see this is seems to be a very natural generalization of the potential game. In particular, in the potential case, this essentially means that alpha is equal to 0. Okay, but this is actually a crucial and an important generalization, because once you allow for this additional parameter alpha, then you can actually analyze this. You can essentially apply this framework for most dynamic game. For example, you can choose this one naive choice of the potential function phi is 0. Okay, in this case, you can choose alpha just to be the maximum over this unilateral deviation of the cos function. Okay, of course, this is not a very clever choice of alpha potential function, but at least this framework allows you to include most of the dynamic game. So assume that a game is an alpha potential game, then you can essentially the alpha potential game you can have the similar property as the being a potential game, in the sense that if you are able to construct a corresponding alpha potential function, then any minimizer of the alpha potential function is going to be an alpha Nash equilibrium of the corresponding game, in the sense that no player I will be able to improve their objective function up to error alpha through unilateral deviation. So the catch is essentially the same as the being a potential game, in the sense that if you finding an approximate Nash equilibrium in an alpha potential game become an optimization problem of the corresponding alpha potential function. Okay, so in the sense that computing the Nash equilibrium or approximate Nash equilibrium reduced to a single optimization problem of the corresponding alpha potential function. Okay, so a very natural analytical question in this for this alpha potential game framework is that, given a dynamic game, how do we construct a corresponding alpha potential function? Okay, so because that in this case that I show you that this alpha, the quantity about the performance or the quality of this Nash candidate is essentially the same alpha in this definition. Okay, so in the case that I show you previously, that a naive choice of 0, the potential function to be 0, gives you some alpha, but this alpha can become big. Okay, the question is that, can we construct a more clever, a better alpha potential function for a given game, for a given dynamic game? And what is the corresponding alpha, which is essentially going to determine the performance of the minimizer you get from this corresponding alpha potential function? And then third question is that, once you find such an alpha potential function, how do you optimize it, and then in order to compute the corresponding alpha Nash equilibrium? And in our paper, we essentially address these 3 issues. So we show that consider the previous generic game. Okay, you can construct a alpha potential function through some sort of aggregation over all players' objective functions gradient. Okay, so in particular, this means that for each player to construct a potential function, alpha potential function, for each player I, you essentially you differentiate player I's objective function with respect to the player I's own control strategy. You aggregate all players' objective functions gradient, and then you do a certain line integration over this aggregated gradient through the control space. Okay, and then you can actually show that we show that this alpha such a function phi is actually an alpha potential function for this generic dynamic game, where the corresponding alpha can be controlled by the magnitude of this pairwise asymmetry of the second order derivative. Okay, so here I want to emphasize that this alpha depends only on the pairwise asymmetry of the derivative. Okay, for example, if I take an example about me and Beatrice. So in this case, it is basically I only care about for in this case I compute my own objective function and respect to my the deviation of my own strategy and also BS strategy, and I compare to BS objective function with respect to my strategy perturbation and then BS strategy perturbation, and I look at the difference of this asymmetry term. Okay, so it does not involve the homogeneity over all players, but only pairwise, only some sort of pairwise asymmetry. And then in this case, that once you construct such a potential function, you can actually essentially minimize this potential function, and it will give you a corresponding alpha Nash equilibrium. So in the remaining part of the talk, I would like to illustrate this framework and then to do some concrete dynamic game. And in this case, I will show you how the potential function, the alpha potential function looks like, and then how this, going to show you how more quantitatively what this alpha looks like, depending on the game structure. So to illustrate this idea, I will first start from the simplest game. In this case, there are n player. Each player only control their state variable, where they only control a corresponding drift term, and then where there is additive noise. Okay, so the state essentially follows from this controlled SDE, where this noise can essentially be correlated. Okay, so you can think about this is a multi-dimensional state, and this is a multi-dimensional Brownian motion, and with the corresponding matrix sigma. For people familiar with the mean field game, this means that each individual state can suffer from individual noise and also a common noise. Okay, this is allowed because that in this case we are not considering sending n to infinity. We are not doing mean field approximation. We are just doing directly solving the corresponding n player game. And then the cost function involves the interaction through the cost function. The running cost can depend on all players' joint state and all players' joint control. And then the terminal cost can also depend on all players' joint state. So in this case, you can show that you can apply the previous construction. You can show that the alpha potential function becomes this concrete control problem. The state of this control problem is that you just group all players' joint state into all players' state into a joint state space. The cost function, the running cost and the terminal cost of this control problem can be explicitly constructed in through each player's cost function. So in this right now, I haven't assumed any homogeneity assumption in the sense that all the player can have the different running costs and different terminal costs. They can have different state space. They can have a different noise term. So in this case, that the catch is as I said before, in this case, find the alpha Nash equilibrium of the corresponding n-player game, reduced to a finite dimensional of a control by reducing to a stochastic control problem of this potential function phi. And we can also quantify the corresponding alpha in this case. In this case, the alpha will depend on it will be given by this form where it depends on the second order derivative of the difference of any two players' cost function. Okay, as I said before, in general, the alpha depends on the magnitude of the asymmetry of the Hessian term, or this pairwise asymmetry of the Hessian term. And in this case, this is essentially reflected by the case that I'm only looking at the pairwise asymmetry. That is essentially for any two players, the difference of any two players' cost function, and it only involves the Hessian term, which means that it involves the second order derivative. So this is a non-asymptotic bound in the sense that I didn't assume any structure about the cost function, and I didn't assign the number of player n to infinity. If you assume further structure of the cost function, then you are able to essentially get improve this bound and then to get a more precise dependence of the alpha in terms of the game structure. For example, you can consider this case where in this case that this is essentially application from motivated from application of in the automatic driving. In this case, you can think about each player's cost function is each player's state is essentially their the position of their own car. They want to reach to a certain target where this terminal cost GI depends only on the player's I's terminal cost only depends on player I's the position of the player I's state, which essentially penalize how far away their own car is away from their target position. Okay, if for example, if the player I want to go to the position X, you can think about this GI is something quadratic around the position X, where it becomes larger if the terminal state X is away from the preferred target. And then there is this interaction term. In this case, that there is some running cost depending on the cost on the control of the player I, because I don't want to use a lot of effort. And then there is this interaction term. Okay, this interaction essentially specifies the this collision avoidance behavior in this automated driving problem. Okay, so essentially it essentially means that the ki is essentially the kn is essentially interaction kernel. It's defined in this form where rho is essentially a density function which vanishes, goes to zero as the input z become tends to infinity. What it means is that I want to minimize this cost and I want to be away from others. Okay, so in this case, the k is something goes to zero as the input, the distance become bigger. Okay, so I in the sense that I want to make the cost small by make sure that I'm my car is away from the others. Okay, but the important part is essentially this how the precise impact of the player the jth car on my car is essentially given by this interaction kernel, and which is given by this form depends on the number of players in this space or number of cars in this space, and depends on the interaction strength beta. Okay, so in the case that the beta is a parameter between 0 and 1, when beta is equal to 0, then this means that this weight become 1 over n, and then the input just the n to the power beta become 1. Okay, what it means is essentially this is known as the weak interaction in the sense that in this case, because of the decay of this density rho, I'm only care about the players. Roughly, I'm caring of the players with a distance of order 1. Okay, but the strength of each players in this region will essentially the impact on me will essentially of the order 1 over n, and it will vanish as the number of player n tends to infinity. What it means is essentially asymptotically, I don't care about any players any player's position. I only care about the aggregated behavior of all other players. Another extreme is essentially the beta equal to 1, and this is known as the strong interaction. In this case, you can look at this ratio. The beta minus 1 becomes 0. In this case, that this ratio become order 1, and then the input will have become there will be a scaling of n. What it means is that as the n increase, because of decay of the rho, asymptotically I only care about the cars in a smaller radius, where the radius is of the order 1 over n. Okay, so the interaction become much more local, but the strength remains to be the same. So for any player which is in this target region, in the region I care about, I still care about their deviation, and then their impact on me does not vanish in this case. Okay, so in this case, it is in the interacting particle system. This is called a strong interaction, and the people believe in this case there is no law of large number. So in the sense there is no mean field approximation in this case. And but if you apply this cost function to the previous generic upper bound of alpha, we can show that this in this case the alpha is actually zero, no matter what the beta no matter what the beta is. So in this case, that for both the weak interaction and the strong interaction, this corresponding n-player game become a potential game. In a sense, if you minimize the previous cost function, solve the corresponding control problem, you are going to get a Nash equilibrium of the game. So in this case, okay, I don't need to. I can allow for different player to have different target position GI. They can have different penalty for their own control, and I don't need to impose a homogeneity assumption in this case. So roughly speaking, in this case, the alpha quantify essentially captures the intensity of the interaction in this case. We can also apply to show this fact in a more explicit way. We can consider a case where the k is essentially independent of n, and but we allow the interaction to be heterogeneous in the sense that Qij specifies how player I care about the player J's position. Okay, so the k is essentially models the interaction, and then the Qij model reflects the interaction strength. In this case, you can apply this particular cost function to substitute this particular cost function to the previous upper bound, and you can show the alpha is essentially given by this form. It is given by depends on the curvature about the interaction kernel, and also depends on this pairwise asymmetry of the interaction weight. Okay, so in particular, if the interaction is pairwise symmetric, in the sense that if you put all the interaction in terms of a big matrix, and this matrix become a symmetric matrix, in this case, the alpha is zero. Okay, so in the sense that it is a potential game, and then finding the corresponding solving the corresponding control problem give you a Nash equilibrium. Okay, this of course include the mean field case. In the case that all the Qij are essentially identical. It also include the symmetry network any symmetry network case. In particular, it includes the graphon interaction, where it is typically assumed that the interaction is given by some dense symmetry network. This framework also allows to capture a sparse network and with asymmetry interaction. For example, you can assume that each player's interaction are essentially given by a graph with a bounded degree, a d. In this case, that as the number of players increase, basically interaction become more sparse. Okay, and it is for people for experts who are familiar with graphon approximation. You know that basically this bounded graph is actually challenging to have a graphon approximation. So in this case, you can assume that this pairwise interaction asymmetry decays exponentially depending on the graph distance of any two player. Okay, so this Cij essentially is the graph distance, means that according to this interaction graph, how many steps the player I need to use in order to reach player J. Okay, and we assume that this interaction essentially decays when the player are really far away on this graph, and then the precise decaying speed is given by this parameter rho. In this case, you can essentially apply this essentially use the previous upper bound of alpha. You can precisely quantify how this alpha decays with respect to the number of players, depends on the degree of interaction dg, and depends on the speed of the interaction decay, which is given by the rho. Okay, so asymptotically, as the number of n tends to infinity, okay, now solving the corresponding solving the corresponding control problem give you approximate epsilon Nash equilibrium of the n-player game. You can also generalize the result. Instead of having this exponential decay of the asymmetry, you can relax it to be the power polynomial type of decay. In this case, that the alpha also vanishes, but instead of in this polynomial rate, it vanishes with the logarithm rate. And this has also there's so a group of economists, they also take our framework and apply to random networks. And in this case, that the weight are essentially generated by some random graph. they are able to show that if you consider a random graph which is sparse and or dense, then the alpha goes to 0 as the number of player n tends to infinity. So before introduce further analytical result, okay, I want to show that essentially finding the corresponding alpha Nash equilibrium becomes solving this control problem. Then there are many tools you can use to characterize a solution of this control problem. For example, you can use verification to characterize the optimal control and the alpha Nash equilibrium through a finite dimensional AJB equation. Then you can show that this Nash equilibrium is essentially has a Markovian representation. And using this Markovian representation, you can numerically solving it by essentially approximating this phi by some neural network and then directly minimizing this potential function over such a policy. And then which allows to give you some efficient numerical method to find the corresponding alpha Nash equilibrium of the n-player game. And I want to show you give you some numerical illustration about how this interaction will behave. So, okay. So this is the first case. Okay. So this is in this automated driving example where there are 10 cars. Okay. They all start from the same spot, the same starting point, and they all want to reach to the same target. Okay. But as I said before, when they move, okay, they want to deviate from others. Okay, and then the precise interaction is essentially given by this interaction kernel I mentioned before, and depends on this parameter beta. Okay, when the case of beta is equal to 0, then it is essentially the mean field regime. In this case, it is a weak interaction, and this is essentially what this plot shows you. Okay, what you can see is that you barely see a deviation from the all players trajectory. Okay, this is just because for this particular choice of the parameter, because of weak interaction, as the number of players is large enough, you only care about the aggregated behavior rather than each individual position, and this is not enough to essentially to ensure a collision avoidance. Okay, and this is essentially what the people in automatic driving problem they want to see. However, if you consider this stronger interaction kernel, this is exact same setting, but in this case, the interaction become stronger but become more local. Okay. In this case, you can see that all the cars start to deviating immediately at the beginning because they want to have their own space, but overall they eventually reach to the target. You can also apply to have certain obstacles. In this case, there is a gray area where you don't the class does not want to go. Okay, but you can see that by introducing this state constraint, the cars essentially basically Nash equilibrium trajectory essentially it changes because they want to avoid this obstacle. And all these numerical results are generated by essentially using policy gradient formula, policy gradient algorithm to solve the corresponding control problem. So I want to in the remaining few minutes, I want to mention that so far I have tried to illustrate this idea from based on this simple dynamic game where there is only interaction over the cost function and each player only control the drift. But you can actually apply in our paper. We actually applied this. We actually lay down the theoretical foundation for the generic games, where each player state the drift can depend on all players' joint state and joint control. The drift can also depend on all players' joint state and control, and there is also interaction through the cost. In this case, you can still write down the alpha potential function by computing the gradient of each player's objective function with respect to their own control, and then do this aggregation over the control space. But the cost function and the potential function become much more involved because of the interaction through the state. In this case, basically this potential function involve a y, which is essentially a sensitivity process of the player's ice state with respect to their control. Because of that, we are essentially using a chain rule to compute the gradient of the objective function. And then this potential function involves a certain aggregation over all players' control over the control space. Minimizing this potential function, finding the corresponding minimizer of this potential function will be technically more involved. We essentially provide a verification theorem by lifting this optimization problem into a controlled Marquin-Vlasov problem. And then we essentially characterize the solution by using an AJB equation on the space of space of probability measures. In the linear quadratic case, this infinite dimensional AJB equation can be solved analytically using a system of ODEs. And then the corresponding alpha can be bounded using similarly as before, but in terms of number of players, in terms of the state coefficient, because there is interaction in the state, and also involving the gradient of the cost difference. And in principle, this framework can also be applied to more general games where you can have nonlinear dependence of the objective function on the law. Okay, so we only studied in this concrete case which is essentially appears in the mean variance portfolio optimization. In this case, that you can think about there are n players. They essentially trade in a common financial market. There is a risk-free like a bond where it has a risk-free rate R, and there are D risky asset where the price is essentially follows from this geometric sort of vectorized geometric Brownian motion, where essentially the return can be driven by the same by some correlated Brownian motion. It can also be driven by some Poisson Poisson random measures. And then each player essentially consider their discounted wealth process, which the UI specify player I's investment strategy in the sense that how much dollar they invest, the player I invest in this risky asset. And then you can show that by the corresponding discounted wealth is essentially given by this follows from this controlled jump diffusion process. And then player I try to maximize this mean variance objective in the sense that relatively to other players, in the sense that player I want to outperform the other players' terminal wealth through this aggregated form. And on the same time, I have a certain penalization over the deviation over this performance gap. Okay, so here lambda ij and the theta I and the psi j, they are just some positive parameters. Okay, we show that for general parameters, this game is actually a potential game. Okay, in this case, that basically you are able to write down a corresponding potential function, which is a linear quadratic Marquin-Vlasov control problem, because here this involves nonlinear dependence in the law. And then we are able to show that because it is a potential function, any optimizer of this linear quadratic control problem is a Nash equilibrium of the corresponding game. And then we show that under certain condition that which depends on this interaction in the right term, then this corresponding linear quadratic control problem has a optimizer, and then you can find the corresponding Nash equilibrium of the game. And this Nash can be solved explicitly in terms of the feedback form. And you can, if in the literature, this such a mean variance portfolio game is typically studied in terms of the mean field regime. In this case, that this size A is depends on everyone has the same size A, but in our case, we relax to more general size. So in summary, in today's talk, I present an alpha potential game for solving n-player dynamic game. The advantage of this alpha potential game is that it avoids passing to the n-player, passing to the limit as n tends to infinity, and it allows you to reduce solving this alpha Nash equilibrium in terms of minimization of the corresponding alpha potential function. The alpha we essentially construct alpha potential function analytically, and then we analyze this alpha in terms of explicitly in terms of number of players, in terms of strength and degree of the heterogeneous interaction. And I want to quickly mention that some open question in this framework. We just start work on this 2 years ago, and then we think that there's a lot of interesting questions in this area. The first is that, and as I said before, the construction of the alpha potential function and alpha for a concrete game is essentially non-unique. Okay, so in the sense that in our work, we essentially give one specific choice of the alpha potential function, and then we quantify the corresponding alpha. But for a given game, maybe it's natural to ask whether we can get a better alpha potential function. Is there a sharper estimate corresponding alpha? And then whether you can use through different construction of the corresponding alpha potential function, whether you can construct a corresponding different Nash equilibrium in this case, and then what is the property of the corresponding the alpha Nash equilibrium. Another interesting question is that to leverage on this computational advantage of this alpha potential function to design algorithm to solve the corresponding games. So in a recent paper with my PhD student Philip, we try to do the first step in this area. We show that if you know in a linear quadratic game, okay, in general the policy gradient may not converge. But if you know this linear quadratic game is an alpha potential game, you can actually show that a policy gradient algorithm will converge to approximate Nash equilibrium, where the quality of this Nash depends on the alpha and depends on the interaction in this game, as I showed you before. And we think that there's a very natural question is that whether the same result holds for more general dynamic games, and it will be interesting to explore. Thanks for your attention.
Thanks a lot, Yufei, for a great talk. So we have a few questions in the Q&A, which probably you can see. Maybe if I can have a quick one, because I think you started answering this in the last slide, because you started at the beginning, said that one of the drawback, right, in the classical Milfing game is also the computational complexity, right? And here I wanted to say, because now that you have heterogeneous agents and they have different kind of interactions, if you can say something, because when n is large, I can imagine that this is a nightmare to. How much does this depends on the degree of symmetries, or if you can say a couple of words there?
So actually, in our paper, okay, so I think it's a good question. So in order to the computational complexity depends on two parts, in my two aspects. The first is when you have a large number of agents, it depends on how do you parameterize your feedback control. Okay, if you have a large number of agents, I need to parameterize to all players feedback to all players state. This will have an increase of complexity. The second is that once you have a fixed such a feedback structure, how do you design an iterative algorithm to find such a corresponding Nash equilibrium? So in our paper, we essentially analyze this property in the linear quadratic case. And in this case, we only focus on the distributed equilibrium in the sense that in this case, each player only perform feedback to their own state. Okay. In this case, the complexity in terms of policy parameterization scales linearly, because that the number of essentially because each player is only feedback to their own state, and the computational complexity to find such equilibrium, distributed equilibrium, I think it is independent of the number of player because of the potential structure. So overall, the computational complexity will scale linearly. So
okay.
Yes.
Yeah, sorry, I didn't want to take too much time because I know there are several questions pending. Can you read the Q&A? If you cannot access this, I will read it for you.
I don't see. You can see my screen. I don't see the questions that all the chat. Or maybe
You don't
there's
see the Q&A.
Oh, Q&A. I see. Okay. So the first question is maybe I can say, under what condition on the state dynamic cost function interactional does a given n player admit a potential function? is the characterization of the sharply exact potential as the single condition of the. Yes, so this is, we somehow already answered this a little bit in the sense that to meet alpha potential, so to meet an alpha potential function, this does not require any structural assumption, right? You can have alpha, you can have a non-asymptotic alpha, depends explicitly on the asymmetry of the cost function. In order to make this alpha to be relatively small, then we give us a few examples, depends on the asymmetry of the, depends on the pairwise difference of the each player's cost function, and then with respect to their Hessian. I hope this somehow already explains a little bit about how the alpha view scales in terms of the game structure.
Yeah, the list. I let you go through the list if you
Yeah,
can say a couple of words about
yes, another question is for n player to stochastic control the reduction to scenario for the alpha potential is powerful. However, the alpha is a function of all player state. How do you implement it in practice? Yes, so this is essentially what I illustrate before. So then it depends on how do you parameterize the feedback function, right? Basically the policy parameterization. But I think in practice these days, if you are able to get access to a good computational machine, a device, and then people can easily solve hundreds or even thousand dimension of control problem by policy gradient algorithm. So in some sense, solving to solve a high dimensional control problem using a neural network is relatively, I think it's mainly about a computational device rather than, so I think it's relatively affordable in this case. So in alternating with the transient price impact, does the alpha potential function C depends corresponds how can alpha be interpreted transient? Okay, this is a very good question. We haven't explored this. We thought about this, but we haven't explored really applying this alpha potential function to the optimal execution problem. It will be interesting to see that and then to see how the alpha scales. So if you are you are interested, I'm happy to discuss more. Yeah, we haven't analyzed this. It is an interesting direction. So thank you. Is it possible to extend the framework to non-local operator with the interaction with intervention or impulse controls? I think it is okay. Right now, I think for the singular, it depends on the structure. Uh, we thought about that for the singular control, we can, it depends on, I think that the things will be much easier, which we now have a relatively concrete answer, is that if the interaction is only through the cost function. In this case, that we basically you can more or less apply the same framework to apply to have to construct a corresponding alpha potential function. If the interaction is through the state, as I show you in the last part of the talk, the construction of alpha will be more challenging, and we haven't thought about it. So as I said, this is just at the beginning phase of this new framework, and it's good that you have a question, and I think it was well to explore that. Is the small uniform upper bound alpha and some condition? Yes, or is that the smallest uniform upper bound? Okay, and under what cover does this mean that each individual player may have optimal strategy that is not unique? Yes, okay, I think a very good question. So the first is whether there is a smallest, whether it's the best alpha. It depends on how do you define the best. Okay, I think in the previous paper by Xin Yu and Xin, where they first proposed this alpha potential game framework for a discrete time game. Okay, in this case, they consider the so-called best alpha in the sense that if for any given potential function, they find corresponding alpha, then they also optimize over the family of potential function. They have an algorithm to show that this optimization problem this big optimization can be solved by some linear programming approach. It will be interesting to explore this how the things whether you have a analog result in a continuous time setting, and then more interesting what is there is an analytical structure about the best potential function. I think this is a good question, but we right now we haven't worked on we haven't analyzed that. So we only have some thought. Yeah. So does this mean that yes, in this case, as I said, for different potential, different alpha, for different construction of alpha potential function, it may lead to different minimizer. And then in some sense, it gives you a different alpha Nash equilibrium. Only in the potential case that we know that all the potential functions are equivalent. And in this case, that you may still have multiple minimizer of the corresponding potential function, but then in this case, you had multiple Nash equilibrium in this case. And how to through different construction. So basically, how does the quality or the performance of a particular Nash equilibrium depends on the corresponding alpha potential function? It's an interesting question, but I think it is worthwhile to explore. For any MFE obtained as minimizer of the Can any MV be obtained as minimizer some a mean field equilibrium when any alpha approximate? I think okay, thanks Dirk. The first one is that no, not all mean field equilibrium can be obtained as a minimizer of some potential. Because that in general, I think there is a relatively well-known example in the mean field game, in the sense that there is a certain mean field game which is a mean field potential game. There are three minimizer. There are three mean field equilibrium. There are two is a minimizer of the corresponding mean field potential function, and there is one which is not a minimizer of the potential function. Because in general, in order to find a Nash, you don't need to find the minimizer of the potential function. You just need to find a suitable saddle point where there's no player can unilateral. It's more like a local optimal in some sense. In this case, that in some sense, not all I don't think not all mean field equilibrium can be obtained as a minimizer. So I think actually this is why um, um, I think Dila has a paper saying that if the only mean field minimizer which is stable, which is the only mean field equilibrium which is stable under common noise perturbation, is essentially given by the minimizer of the corresponding potential function. Any alpha approximate this is interesting. We haven't thought about that. I suspect it may not be true because that if it is because if it is so asymptotically, I think it may. I suspect it may not be true because it's just in the sense that not all equilibrium, not all mean field equilibrium is given by the minimizer of the potential function. Can you comment more on the relativity on the asymmetric graph, a graph form, or given a reference? I don't know what you have in mind, Dirk, for this, for more details. I think we basically we only comment these two cases. And if you are interested in a more precise graph, yeah, maybe you can send me an email, and I will try to send you the reference I know. Yes. I think this
Thanks a lot. So let's see. I think, yeah, we have been answering all the questions. So if there are another questions, I think we're all very happy to listen to you. So thank you for the talk. Thanks everybody for the question. That makes really this, even more interesting to exchange ideas. So let me see. Sorry, I see just one pop up. There was maybe one last just now. I'd appreciate if you can comment on how to determine the best alpha.
Yes.
And this will be the last question. Let's retake.
Yes, it's the last question. This is, as I said, that in the discrete time game, you can essentially the optimal alpha. One way to define the optimal alpha is to essentially say that I'm going to consider optimal alpha within a family of potential function. Okay, so basically for any given potential function, you can look for the best alpha by minimizing over all the unilateral deviation. And then you perform a max problem by basically you solve a mini-max problem to say what is the corresponding optimal alpha within a family of potential function. And this can only be solved numerically through some linear programming linear programming algorithm. Whether one can do similar things in the continuous time setting, and then whether you can actually have analytical structure about the best potential function, that is a very interesting question. And then it is somehow need to define a way about what to mean by optimal or best in some sense. I mean, it must give some metric to optimize. Yeah.